Hello, everybody. In this video, we're going to go over how to tell if an improper integral converges without actually doing the work to solve it. So this is a pretty handy technique. Now, just to be clear, this isn't going to work all the time. In fact, it's hard to say. This technique won't work for type 2 improper integrals. Well, there's a slightly separate technique that we can talk about. But the simple technique will only work for type 1. It's not going to always work for type 1, but it does enough to be useful, I'll say. So, because think about it, like usually with improper integrals, isn't it kind of handy that if you can just like theoretically tell that the answer is going to be diverge, you can basically skip some work, right? Where you would have spent a couple minutes on the problem. So that's what we'll do today. Let me share my screen to start. Now, the key idea, here's what I'll say. So let's start with type 1 because type 1 is easier. The whole point, the whole problem with type 1 improper integrals, the whole crux of the problem is the infinity going to end up in the numerator or denominator? That's the most important detail. So it's what determines whether it converges or diverges. Now, if it happens to end up in the numerator, or sorry, in the denominator, that means it will that means that it will diverge, or sorry, that means it will converge, and then you do have to do more work to figure out what the answer is. You would have to solve the problem, but for roughly, I don't know, a quarter to a half of improper integral problems that are type 1, the answer is probably diverge, which means you can knock out a lot of those without really doing much work. So here's the question. So that we're looking at a type 1 improper integral. I have infinity in the input. So what does that mean? That means wherever I have an x value, wherever I have the x value after taking the integral, that's what's going to happen. So if I just look at this thing, so think about in your head, what's the antiderivative or the integral of 1 over x? Natural log of x. Well, natural log of x goes to infinity as x goes to infinity. So right there, before we do any work, before we do any of the steps or we put in any effort, we already know the answers diverge. And then let me show you some other ones here. So that one, diverge. Diverge. And also let me show some other ones here. If we have anything greater than that, by the way, so if we have like 1 over square root of x, think about this, like square root of x to the negative 1/2. Again, if you take the antiderivative of that, you get, and again, you don't even really care about the constants just for what we're doing now. You really just care about where does the x end up. So it really, what is the power on the x is another way to think about it most of the time. So like here, if we're starting with x to the negative 1/2, well, think about it. X to the negative 1/2, if we integrate that with the anti-power rule, you add 1, right? So that'll be x to the positive 1/2. X is in the numerator. There you go. End of problem. If x ends up in the numerator, diverge. Why? Because we're going to end up plugging in infinity into the numerator. That's no good, right? And then you can try these other ones too. Like if we have, again, same, you could have the same setup roughly. So let me actually shrink this down slightly. So I'm just going to shrink it down so we can kind of fit more on here. Nope, did not mean to do that. That wasn't good. That's not working reliably. I don't know why. Let me try one more time. Okay, that doesn't want to be shrunk. So maybe this will. Okay, shrink that. Yeah, sorry, I don't know why that's so annoying. So yeah, looking at that, that's also diverge. And then we can do a similar one. Let's say we can tweak. You could basically have just x, right? Well, what's the integral of x? 1/2 x squared. And by the way, you could just look at this and say this is an increasing function, by the way. Remember, if it's increasing or it's constant, it definitely diverges. It has to be decreasing, and it has to decrease by fast enough for it to work. And that's kind of what we're talking about here. So you already know just because this is an increasing function that is going to diverge. So you could just say that. Or if you wanted to, you could do the trick. So x integral is 1/2 x squared. X ends up in the numerator. Basically, the power is positive is another way of thinking about it. So diverge. So hopefully that makes sense. You notice I didn't do any of the work to solve these. You could just look at it and tell if you understand that way of thinking about it. Basically, after you take the antiderivative in your head, if the power on x is positive, it will end up in the numerator, which means infinity will end up in the numerator, which means diverge. That's the whole problem. If the derivative, so like let me give another example. So if we did 1 over or 1 to infinity, and then it's 1 over x to the 3 halves. So think about this as x to the negative 3 halves power. Well, then when we integrate that with the anti-power rule, we're going to add 1 to negative 3 halves. So we'll get x to the negative 1 half, right? That's still negative, which means x is going to be in the denominator, which means when we plug in infinity, it's going to be in the denominator. And whenever infinity is in the denominator, it converges. Hopefully that makes sense why it converges, right? So if I do 1 over infinity, that's roughly 0. If I do 1, or if I do 1 times infinity, well, that diverges to infinity. That's effectively what we're noticing here. That's why this is working. So that's good. So that one we just checked. So that's good. And then we can try other powers, right? X squared. But again, anti-power rule, x to the negative 2 plus 1 is x to the negative 1. Still a negative power. That means x is still in the denominator. That means converge. And then anything beyond this, by the way. And just in case you're wondering, you could test this like 1 over x cubed, 1 over x to the fourth, 1 over x to the fifth, 1 over x to the millionth. Still works. So hopefully that makes sense. Hey, Hardik, how's it going?
Hello.
That's good. I was just going through some improper integral stuff, but I think that you're a ways away from that as well. How's class been going the rest of the week?
It's good. I
Cool.
think I think we're on 6.8 now.
Okay, so 6.8. That's is that you? So you're pat. So you're on. Is that U sub if I remember correctly? Or sorry,
Or it's the non-BC topic, so it may not be 6.8. I don't know.
so
So let's
6.8,
check.
just indefinite integrals.
Yeah.
Cool. Is everything making sense in class? Like, do you feel like you understand everything?
Yeah, everything was making sense.
Cool. Sounds good. How's your studying ahead going?
It's been going good. Like we skipped the 6.4
Mm-hmm.
and 6.5, so I did those already.
Okay.
Because
Yeah,
he
so
wants
the
to focus
accumulation
on.
functions, those are kind of tricky. I have something that'll help with that, by the way. Um, just as an FYI, if you go to Skool here, so or not that, if you go to this, and you check out the classroom tab, check out the resources, and you should be able to search here. By the way, you should be able to search for whatever the topic is, but it should be here you go, accumulation functions. This Desmos animation is pretty helpful
Mhm.
to understand it. So we can talk about that now if you want, but I know it's a tricky topic,
Sure.
but so this animation is handy. But basically, the idea. Let me make a tweak to this. Yeah, just make it a little easier. Basically, the idea. I'll change the a value to 1. Let's say. So let's set that to 1. So basically, see if this makes sense. Do you agree? Or I'm just gonna change this. Do you see how as I move, and I'm going to turn off the orange one for a second, but we start off with some function, basically, like sine of x. And then do you agree that as I move to the right, you see how this is why it's called an accumulation function, because as we move to the right, we accumulate more area under the curve.
Hmm. Yep.
Now here, what would you say, like just right now, it doesn't have to be perfect, but about how much area have we accumulated under the curve, would you say?
Uh,
It just is a rough estimate. It doesn't have to be perfect.
two, like 2.5.
So you're saying this green area is equal to 2.5?
Perhaps, yeah.
So think about this. What is the whole white square equal to in terms of area? Like what's this whole square
Oh,
equal?
it's 1. Okay,
Yeah.
yeah,
So that'd be 1 unit squared, whatever the units are.
yeah.
So we have about what for this green area?
Like half of it.
Yeah. So basically half. So in other words,
Yeah.
the area that we've accumulated right now is about 1/2. And what is the height of the orange value? You see how it's also about 1/2. It's not perfect. It's a little
Hmm.
bit under, right?
Yeah.
And then if I keep going to the right, we've accumulated more area. So now does it make sense that we're about again a little bit less than 1 because we do have this white space, right?
Hmm.
So the area that we've accumulated so far is about 1, whereas this what's the height of the orange dot?
About 1.
Yeah, the area that we accumulate is equal to the height of the orange dot for all values of x. So here, as I keep going, I'm accumulating more area. The orange dot's going up. accumulate more area, the orange dot's going up and up and up until it gets right there. It hits a maximum. And then you see how we start accumulating negative area, which is going to decrease our total amount by a little bit. And now the orange dot's going to start going down.
Isn't the orange dot making a function?
Yes, it is. That is what the accumulate, and I'm going to turn it on now. So yes, that you can see, just to redo everything we just did, that's what was happening. Yeah. So the orange function is the accumulation function. It is a function that tells you for any x value that you could plug in, how much area have you accumulated under some other integral, some other function. And then
Okay.
whatever the area is, that's the height on this function. That's the output on this function. That makes
Okay.
sense.
That makes sense. Yeah.
A little abstract, but that's the idea. And then here kind of makes sense when you get here, right? Because the green and the red cancel out. And then when
Yeah.
you go here, it's going down and down. And then we start adding positive area. So we stop going down, start going up again. And then here, this is where everything's canceled out again. So yeah, it's basically like that. And this is like the orange function is essentially the antiderivative of the original function. But here's another way you could look at it. You can look at it as if the purple one is the derivative of the orange one. You know what I mean? Like here, for example, you see how we have a relative maximum. So positive
Hmm.
slope on the left, negative slope on the right, positive value on the left, positive value on the right. The
Hmm.
purple one is the derivative of the orange one. And the orange one is the antiderivative of the purple one. Two
Okay.
different sides of the same
Yeah.
coin. So there you go. That's help. This is really helpful. Like when you're doing your homework problem, like if you're doing homework problems on that, you can also try this out, right? You just choose your A value, choose your B value, choose your function, and it'll help you visualize it, and it will help you calculate what the accumulation is. So that's pretty handy. One other thing that's weird with these is that you can go backwards, right? So if you're right here and then you go backwards, you see how we're accumulating negative area, and then our
Hmm.
area under the curve is negative.
Yeah.
So that's something worth paying attention to as well. When you're going backwards, do you get why that is? By the way, because when you have the bounds, if the upper bound is less than the lower bound,
And
there's
it's
that
negative
integral
being
property. Yeah,
together.
it's like you flip them and make it negative. That's what's happening here. So it's like the
Mm.
areas that are above the x-axis actually happen to be negative now. The areas that are below, they actually happen to be positive. So it's kind of a weird setup, but
Yeah.
yeah, that's what's happening. So this animation is handy to kind of visualize that. But yeah, that's the basic idea behind animations, or sorry, but behind accumulation functions. I'll say.
Hmm.
Cool. Sounds good. Did you have any particular questions that you wanted to kind of go over today?
Um, let me check real quick. The you know the fundamental theorem of calculus,
Yes.
the
Part one.
where it's like I think it. I don't know. He said part two, but I think this is part one.
Yeah,
Most
it's
likely.
different in most classes. They would well, what I'm writing now, they would call that part one. But I have seen like a handful of classes where they call it this. They call it part two. And to be honest, I think it makes more sense to call it part two because it's kind of less important than the other one. But is this what you're talking about?
Yeah, but the bounds were from a function, so like h of x to g of x. That was
Oh,
like a
gotcha.
kind of I was confused about because you used a chain
Yeah,
rule.
yeah, that's
That
tricky.
that was that was
Yeah.
like I couldn't get it conceptually, like how
Okay.
you
Yeah.
multiply to the entire accumulation.
Yeah, that's a good point. So that is tricky. Let's go over that because that's worth going over. First off, do you get the simplified case?
Yeah,
Basically,
yeah.
you just plug in X. And by the way, I'm going to add another video here. This is not my video, but I highly recommend checking this out. This is let me grab this actually. This is you want to check this out for sure. But I'll just link it here. If you check out this video, like I said, it's not mine, but this will go into a lot of the theory. This will go into like the geometric reason or the animation behind why this is
Why this
true.
is true.
But the bottom line is you can just remember that it is by you basically you plug in x with t. It's like like the way you can kind of look at it, the derivative and the integral cancel out, right? And then you just plug in x for t. That's kind of what it seems like happens. There's a deeper
Mhm.
reason behind it. This video goes over, and you don't even have to watch the whole video. It'll jump to the right timestamp where it explains it. But I'll just say that. And it's kind of one thing that's weird is like it really doesn't depend what this number is. You know what I mean? Like this could be 3, it could be -10, it could be like this doesn't affect.
Yeah, because then the derivative will then make it 0, right?
Yeah, that's kind of why.
That's
Yeah,
how I
that's
thought
kind
about it.
of one way of looking at it for sure. So that's good. Now, um, what you're asking about is the harder version. Let me do let me build this up for a second because it's worth seeing here. So let's first talk about a slight tweak. So let me do this to start. Let me say that capital F of x is equal to the antiderivative from 1 to x f of t dt. Right, dude?
Mhm.
I'm just naming this inner function as capital F of x, and then see if this next part makes sense. See if I guess how should I word it? Basically, do you agree that another way of writing what we said above is that the derivative of f with respect to x is equal to lowercase f of x, right? That's just a
Yeah.
short if I'm naming it this. So that's
Mm.
one thing you can say. And then now, let's see if this makes sense. If you have if you have this situation where it's not x in the upper bound, again, we'll build up to what you said. What you said is actually the most complicated version of it. But if you have g of x, right, instead of
Mhm.
x, do you agree that you can look at this situation as the derivative? Again, look at thinking about how we named it here. This is the key insight: is that you can look at it like f of g of x,
Yeah.
one function inside of another. So it's like because again, the normal function is just here's where the input is. It's actually the upper bound of some separate integral, and here we're just substituting an entire function inside of that. So the key
Yeah.
insight is you can look at this as essentially a composite, what's called a composition of functions. One function stuffed inside of the other, and we have a specific rule to take the derivative of that. You mentioned it
Chain rule.
before, chain
Yeah.
rule. You have one function inside of another, you do the chain rule. So that's right. So what's the chain rule? Derivative of the outside. So derivative of f, it's still evaluated at g of x dx. So, and
And then
actually,
G prime.
I'll tweak it a little bit. I'll just say capital F prime to make it easier. Yeah, capital F prime evaluated at the inside, right? Times g prime of x. Well, what is f prime? We already established right here. This is the first fundamental theorem that well, capital F prime is just lowercase f. So that's where you get f
Mm.
of g of x, little lowercase f of g of x times g prime of x.
Mhm.
Does that make sense? Where the like that
Yeah.
way of looking at for the chain rule. So this is kind of the adjusted version, I'll say. So that's good. So basically, it's basically the same. You still take whatever, like this could be, you already know, I assume. It could be like x squared, x cubed, whatever.
Mhm.
You still just plug that in for this, right? So whatever the function is, you just plug that in for that, and we can do some problems maybe to make it less abstract. But let's say that's x cubed, and this thing's like sine of t. I'm just making this up. Well, then this thing would just be sine of not t, but x cubed. So basically the same, right? If like the old way, it would be x instead of x cubed, but you still just plug it in as normal. But then you just take the derivative of the upper function, which in this case would be 3x squared.
Yeah.
That makes sense. And by the way, think about it like this: when we used to be doing x right here, when it just said x, you can still think of this formula. It's just that the derivative of g is now one. You know what I
Oh,
mean? We're
okay.
just multiplying by one
Yeah.
on the outside. So this formula has always been true. You've just ignored it because the derivative of the inner function happened to be one. So it didn't change the answer if you ignored it. Now they finally introduced the harder version.
That makes sense.
So that's the idea. Now your problem is even more complex than this. So there's actually something else we need to understand before going there. Let me ask you this: how would we do this problem if we had like let's just make it simple or simpler. It's not easy unless you know how to do it. Everything's easy after you understand it. How would you do this thing? How would you deal with this accumulation function?
Um, wouldn't it be negative f of x?
Yeah, you need to do that property where you flip them basically, because in order to
Yeah.
use this, the upper, like the way the logic works, and again, the video kind of explains why the logic is that way. But the way the video works Yeah, you have to have the upper, or the way the theorem works, you have to have the input as the upper bound, like that's got to be the function. So yeah, you basically flip it negative. So now let's put all these pieces together, because what you're dealing with is the most complex situation that can happen. It's really a combination of all the tricks we've talked about and one additional one. So correct me if I'm wrong, but this is, I think, what you said. So you said the integral from like g of x on the bottom, some function of x, and then h of x on
Mm-hmm.
the top, f
Yeah.
of t dt. So the thing that's weird, and this is a little new, we have we don't have a constant. Like normally we have a constant on the bottom, which is ideal, or the top, and we just flip it. That's not ideal, but we can flip it. Here we don't have any constant. We have functions on the upper bound and lower bound, which is significantly more
Mhm.
complex. There's every we're going to use everything we've talked about so far, and one additional trick. Do you know what the additional trick is going to be?
No, like the subtraction.
Split, or
Oh,
not
subtraction.
subtraction. Are you aware of that property where you can split integrals in
Yeah.
the middle? Basically?
Hmm.
So do that. Just split it wherever you want. It doesn't even matter where you split it. So
Like g of
here,
x to 0,
yeah,
and then
exactly.
okay,
G of x to
I
zero.
see,
That's
and
the
then
magic
0 to
trick.
h of x.
Yeah. So plus, so it's like we're splitting it at zero in h of x, 0 to h of x, like that. Do you agree with that so far?
Yes.
And then you flip this one, 0 to g of x, make it negative. This one's still fine. And then you take the derivative of the whole thing. So derivative with respect to x. And now you can use this formula, right? Just do the normal way and then chain rule it. So this will be negative f of g of x times g prime of x plus f of h of x times h prime of x.
Okay,
And
that makes sense.
there's a much more complex geometrical interpretation of this. It's kind of like what he talks about in the video here. This is not me, I said, but this is three blue, one brown. I don't know. Have you ever heard of him on YouTube? Three blue, one brown.
No.
You should check it. He has the best animation. He has the best math animation videos on YouTube. Problem is that he talks about really, really complicated stuff. This is like an older video, but he basically kind of created this niche on YouTube of like these high quality math animations to like visualize things better, and they're very helpful for calculus. So that's the video. But it's like the reason there's a certain logic to why this formula is true, but it's even more complicated than what he talks about in the video. Basically, I'll say if we have an accumulation function, I'll just give you a very, very vague idea of what's going on. But if basically we have an accumulation function or we have an area where the top and bottom are changing, right? The top and bottom are changing as functions of, basically as functions of x. So basically what it's asking is, okay, if we make x a little bit bigger, what happens to the total area? If we make x a little bit bigger, we're actually going to subtract area from the bottom, right? Like, does that make sense? If I make x bigger, we actually end up losing area on the bottom. That's why this is
Yeah.
negative. Whereas if we make x a little bit bigger, this thing gets bigger. So we add area there, which is why the h1 is positive. It's a lot more complicated than that, but once you watch that video above and you like, maybe hopefully this should make a little bit more sense. But the bottom line is you don't really need to understand the concept to use it. Like, this is the right formula and this is the right logic for how you can do that.
All right, that makes sense.
Sounds good. Cool. So I think,
Yeah.
yeah, we have about 1 minute left or so for the live today. Any
All right.
other questions or any other kind of burning questions? Remember, you can always also post in
I
Skool.
mean, um, Unit 5, I think
Hmm.
I did bad on, like, test-wise,
Okay.
but I think maybe I should just review Unit 5, and I should be fine because it came back today, when I was doing 6.5 or si yeah, when during the accumulation functions one
You came
because,
back to school, you mean? You mean you were out of school?
no, 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 I mean, like, when I was doing it, in the accumulation functions unit, like, it was, there was the Unit 5
Oh, I
stuff that
see.
came back.
Oh
Like
yeah, I
it's the
see. I
opposite
see.
at
Yeah,
the
yeah, and that's kind of what I was talking about before. Okay, I get what you're saying now. So yeah, that makes sense. So yeah, I would definitely review that again. If you have any questions on that, feel free to pop into our lives during the week, or
yeah,
just ask in school, and I can anytime you get stuck, I can answer. But yeah, overall, that sounds like a good idea.
no
Cool.
problem.
All right,
Perfect.
sounds good.
Thank you.
Good seeing you. Happy Friday, and I will catch you next Monday.
Thank you. Have a great day.
See ya.